So today we are going to start a new section, which is the emerging memories. This is like an overview, and later we will have individual lectures on the specific technology. But today is like an overview of the emerging technologies. So here we are going to discuss some candidates for the emerging non-volatile memory. And then we will focus on the array architectures and then design considerations, including the selector device, which is not a memory element, but it's necessary if you want to do this crossbar 3D point memory. So we will talk about that as well. So if you recall, we showed the memory hierarchy at the beginning of the semester, right? So this is a well-known architecture. And we have those different levels in this hierarchy. And SRAM for the cache, DRAM for the memory, and then the NAND flash for your storage, like the SSD. And then we do have those distinction between volatile versus non-volatile, on-chip embedded versus off-chip standalone. And then we do see the gaps between the levels. So then that brings the question, do we have the opportunities to change this hierarchy by filling up those gaps, okay, with new technologies? Okay, that's the question. So you see those gaps pretty large, orders of magnitudes. And then the question is whether we can, bridge those gaps. So here, if you think more, let's say, broadly, without that hierarchy, if you just want to have a single memory technology, those would be the ideal attributes, okay? So this is your wish list. If you want to develop a new technology, so then this is all your wish list for the memory device. So you need the non-volatility, ideally, and high density, low power, and bit addressable, writable, and then fast speed, non-endurance, and low cost, compatible to the CMOS, and so on. So this is a non-list. And unfortunately, I can tell you till today, there's no such universal memory exists. So you have to make trade-offs basically between those attributes depending on your application. That goes back to the hierarchy. That's why we have different technologies for different purposes in the memory system, right? If you have a single solution like this, you don't need that hierarchy. You can just use one level in the system. So it's all engineering problems, trade-offs, okay? So if you look at the mechanisms to store the data in the semiconductor, so here you rely on the hysteresis, okay? You need some hysteretic property as memory, right? Because you need to remember the state, right? If everything is linear, then you cannot distinguish. So here, if you look at the mechanism, that means some physical mechanism. So here, for the mainstream technologies like DRAM, SRAM, flash, essentially is a charge-based memory, right? Moving electrons, or let's say charge, right? For example, your DRAM has the charges on the capacitor, right? That capacitor is external, it's what you fabricate. But even for SRAM, the information is stored as a charge because you have the coupled latch. Essentially, the parasitic capacitance to that storage node, your Q and Q bar, you have the junction capacitance and then the gate overlap capacitance. So all the charges are held in that storage node, okay? And the flash, we just talked about the flash, right? No matter it's floating gate or charge trap transistor, you store the charge in those trap sites, right? So in the gate stack, you store some charges. So essentially, those are charge-based. And then if you look at the emerging memories we are going to discuss today, many of them involved moving the atoms around instead of the charge, electron and holes. So the emerging memories try to explore the possibilities to move the atoms, okay? So for example, here you have different mechanisms to change the resistance. So here we are going to discuss that in the following, like phase change, conductive filament formation, spin transfer torque, spin orbital torque, and so on. We will discuss that later. And also, you may change the capacitance, for example, the ferroelectrics. So in general, you have to move the atoms around in those emerging memories. So that's a big difference, okay? That also introduce some fundamental limits for the emerging memories. As you can imagine, is it easier or more difficult to move the atoms compared to move the charges? Which one is more difficult? It's more difficult to move atoms, right? So that brings a trade-off, okay? Charges are easier to move. That means it may also easier to lose, okay? So that's why you can have the retention and other issues with the charge. But it's fast and lower energy to move the electrons, okay? Then if you move the atoms around, once you move it, then it's more stable, more better reliability and so on. But then it's more difficult to move. Therefore, you may need longer time, larger voltage, larger energy to write the data. So fundamentally, there's no way to get away of this trade-off. Okay, so then let's talk about the challenges for the charge-based memory, which we just reviewed, right? SRAM, flash, DRAM, the charges are stored either here or in the gate stack. So as we scale down the technology node, as you can imagine, right? So the size or the area of those storage nodes shrink. So the number of electrons reduce, right? So that's why we have this few electron problem in the flash we just discussed. And also in the SRAM, if you look at the single events effect to flip the data by the radiation, then it's easier to flip the data because the area of the storage node, that means the parasitic capacitance also reduce. And then the DRAM, if you do nothing, then still, this capacitance will reduce, right? But of course, we try to engineer to make this capacitor tall and tall, right? So then you try to maintain the capacitance. So fundamentally, we face the challenges to scale because fewer area available to store the charges. You need some volume to store the charges, some area, surface area, or some volume to hold the charges. So then if you do not rely on the charge, right, then you rely on some atoms that could be potentially more scalable, right? So you can rely on the atom configuration to basically determine the states. So let me show you some emerging non-volatile memory technologies at the high level, and then later we'll have individual lectures to talk about more details of the device physics and then the state of the art in terms of the industry, R&D status. But today we just go over the principle. Okay. Fundamentally, you can move just one atom, right? So if you have that atom there versus you do not have atom there, you have two states. Fundamentally, okay. I'm not talking about how you practically implement that. So there are some research demonstrating that, for example, in RRAM research, there's like this quantum point contact experiments and the model for that. So you can place an atom there between two electrodes, and then you make a bridge, and then you get current flow. You remove that atom, then you break that bridge, and then you do not have current. So fundamentally, you can do that. I mean, but how to integrate that into the real technology is a different thing. Okay. Okay, so here, the first one is the spin transfer torque magnetic random access memory, MRAM. And this is STT-MRAM. We're going to discuss different flavors of MRAM later, but today we will show the STT-MRAM because this is in the volume production in the industry right now. And so here, the fundamental building block is called this MTJ, magnetic terminal junction. So simply speaking, you have two little magnets, okay? And those are the typical materials. Of course, the actual stack is more complicated than this one, but to the first order, you have this kind of sandwiched structure. So you will have this magnetization direction, right? Like north pole, south pole, right? Then depending on the orientation, right? So those two little magnets are separate by this terminal barrier, oxide terminal barrier. And then depending on the configuration, if those two magnets has the same orientation, then the tunneling current across this barrier will be higher. So that means the resistance will be lower. Okay, you have larger current across this stack. It's tunneling current. Okay, and then compared to this anti-parallel configuration, then the current is smaller. Okay, so you are based on this parallel versus anti-parallel configuration of those magnetization, then you have different resistance by measuring vertically. Okay, not horizontally. You measure the current vertically, the current flow vertically. Then you have different resistance. So you can use different resistance to store the data, like your data 1, 0. Okay. This is a principle. Later in the individual lectures, we'll talk about more detailed physics, but this is to the high level. And then the phase change memory, okay, PCM. So this one typically use the material based on the chalcogenide family. Chalcogenide is group 6 material. Below the oxygen, you have the like the telluride. So here, typically, it's based on this GST system, germanium, antimony, telluride. Okay, and this typical ratio 2:5 is used. So here, this material has a property that is based on the crystal structure. Okay, if it's ordered, that means if you have these atoms aligned regularly, this is called the crystalline phase. And then by heating this local region, you are going to melt this crystal structure. And then if you quench it, that means you remove the heat source quickly. Then those atoms will, because it's melt, right? They will flow everywhere. And then if you quench it, and then the temperature quickly drop, then the atoms will not have enough time to, return to the original position. So it will be more like a random configuration. So this is called amorphous phase. Okay. So if you measure the resistance of this region, then you have the resistance crystalline phase smaller than the resistance of the amorphous phase. And then how do you get this local heat to the system? Then you need this kind of structure, let's say passing the large current based on the Joule heating, right? you pass current, then you heat up. Then by controlling the current flowing through that device structure, then you can determine the crystalline and the amorphous states. So this is a phase change memory. Okay. And then RRAM, resistive random access memory. So this one depends on the conductive filament between two electrodes. So you have two metal electrodes, and then here you have some insulator, typically oxide. Okay. If you apply large enough voltage, you are going to generate a lot of oxygen vacancy. This oxygen vacancy will be lined up to form this conductive filament, so electrons can flow. Therefore, you have the currents. And also, you can break this filament by reversing the voltage polarity or burn a large current. Then, if the bridge is, ruptured, then here there will be a large tunneling gap. Then the current will be smaller. So, depending on the filaments, you have filaments or you don't have the filament, then you have the different resistance values. So this is a resistive random access memory based on this oxide material. So if you summarize right here, those three emerging memories are all based on resistance. Okay, we call them, in general, you can call all of them resistive random access resistive memory. Okay, but we split that into three because they have different underlying physics, right? Even though externally, when you observe that, you can abstract all of them in the circuit symbol, like a resistor with an arrow, which means resistance can be changed. All of them are two-terminal device, right? So basically, you have a variable resistor here. But the physics is different, or the principle is different, right? So for the STT-MRAM, you one state, on state, typically, let's say you encode one as on state, means lower resistance state, higher currents. And then here you have the parallel magnets there. And then you can, just review what we read on this slide. So essentially, based on the resistance, right? You have 1 and 0, high and low resistance states, or we sometimes also call HRS, LRS, high resistance states, low resistance states. But the underlying physics are a little bit different for those three technologies. Okay, any question? So if you look at the IV characteristic, okay, in general, there are two kinds of IV. One is called unipolar, one is called bipolar switching. So here, because it's a variable resistor, right? Two-terminal device, you just measure the IV voltage across that and then current through that. So then you have this kind of hysteresis in the IV. So for example, in the STT-MRAM, most of the RRAM is bipolar. That means, for example, you start with the high resistance states. When you ramp up the voltage, then because the resistance is high, so current is low. But beyond certain threshold, then the set operation will switch the device from high resistance state to the low resistance states. And typically you have to limit the current by a access transistor or something to prevent some like a permanent breakdown, because the current will be too high if you do not limit the current by this compliance. But after that, if you sweep the voltage back, then you will get the low resistance state, LRS, right? Why this is low resistance state? You know the slope, right? Or 1 over the slope is the resistance. So then bipolar means you have to, if you want to switch back, okay, you have to reverse the voltage to the negative side. So you will go along this one, and then if you sweep the negative voltage, okay, at some points, then the reset will happen. And then the resistance will change from low to high again. And then if you go back, then you will have this kind of hysteresis loop. Okay. So when you read, you don't need to go too large voltage, right? You can just bias somewhere here. Then you can get different currents, right? Then your sense amplifier should be able to detect the difference of the currents. Then you know it's 1 or 0. So unipolar means you're going to only apply the single polarity to set and reset. For example, here, if you only do on the positive side, this happens to the phase change memory. So you just need to have, let's say, here, if you start with the high states, and then you can turn on by this voltage. After that, then it's already in this state. But if you want to turn off, you can apply the same voltage, the same polarity, okay? But then after a certain voltage, it will go back, okay? So this is the IV for the resistance memory, okay? Resistive memory in general. And then let's move on to the ferroelectric. Okay, this is a little bit different. The ferroelectric material has a polarization, dipole up or dipole down. So what is ferroelectric? So first of all, the dielectric, there's a subset called ferroelectric. You know, in the ionized bonding of your crystal structure. So if you apply the electric field, right, all the dipoles within the material will be lined up. And in the normal dielectric, when you remove the electric field, then those dipoles will randomize, and then the net surface, at the surface of the material, there's no net charge, okay, because all the dipoles, randomized. But then the ferro has a property that after you remove the external field, all the dipoles will be lined up, okay. You have dipoles because those crystal structure will have some internal, asymmetry there. So those atoms, depending on the location of those atoms, okay, within one unit crystal structure, you already have some built-in field. That is the dipole, right? Dipole means what? You have like a positive and negative charge, like spatially, separated, right? It's because of those atoms, it's not symmetric. You have some asymmetry there. So the thing is that for this one, after you remove, because you have so many atoms there, right? But then after you remove the material, then those dipoles are still lined up. Unlike the normal dielectric, all the dipoles, they will have different orientation. But for this one, they all lined up. So that means at the surface of the material, you will have the net charge. Okay, that is called the polarization. Okay. So there are different ways to use this property to do the memory device. One is this ferrofets, okay, ferroelectric field effect transistor. So it's similar to the MOSFETs. The only difference is that here in the gate stack, you integrate the ferro material. And then you can have all the dipoles up and dipoles down. That means you are going to modulate the threshold voltage of the underlying channel. Because if you have all the dipoles down, it's like you have positive charge pointing down. That will turn on the channel easily, right? That means what? Threshold voltage will be lower in this state. But if all the dipoles are up, it's like you have negative charge there. It's like more difficult to turn on the channel for N-type, N-FETs. then the threshold voltage will be higher. So the operation will be similar to the flash, right? It's like the IDVG shift. Your threshold voltage shift. Your threshold voltage shift delta VT. Okay. But there is a fundamental difference, okay, in the FE effect compared to the floating gate or charge trap in the flash. That is, the switching direction is just the opposite. So in this IV curve, we call it, if you sweep the voltage, let's say from 0 to some high voltage, then this switching will be this counterclockwise, okay? But if you look at the flash we talked about earlier, it will be clockwise. Or in other words, here, if you apply positive voltage, your programming voltage will lower the threshold voltage, okay? Or let's say positive voltage will lower the threshold voltage. But in the flash, if you apply positive voltage, you're getting more electron trapped. Your threshold voltage will increase, okay? In this case, your threshold voltage will decrease. It's just opposite to each other. So the program erase definition is just reversed. So in this case, the program state actually is this state. Erase state is the other one. It's just the opposite to the flash definition. Okay. We'll talk about that in more details later. Then the other possibility is to use this ferro as a capacitor, like a DRAM, 1T1C. But this C is a ferro cap instead of the normal capacitor. So you can have the built-in like polarization like this. So when you read out the data, you are going to polarize. You have to use a large voltage here. If the polarization is opposite to this voltage, you will flip those dipoles. Once you flip those dipoles, you will get the transient switching currents. So that means, or maybe let's say the other one. Oops. This one, you will flip these dipoles, then you will get large currents to the platelet. So this is transient effect. That is the FE run. And then this is the FE FET. We are going to discuss more details. The difference is that FE FET, you integrate the ferro to the gate stack, and the FE run, you integrate the ferro to the drain contact wire, like 1T1C. Okay, so those are high-level principles. Okay, so then here, if you look at the key metrics of those memories, so here this is a summary that I did. And you can compare the emerging memories versus the mainstream charge-based memory in terms of cell area, multi-bit capability, and voltage, read time, write time, retention, endurance, write energy per bit. So I have to emphasize here, the numbers I quoted here is not the best reported in the literature, but this would be the representative or average number, okay? Because some papers may, push one metric to a very, very good value, but then the other metrics sacrificed, then that's not fair to just pick one good point to this comparison table. So this is a general comparison, okay? So here, we can look at the emerging memories. And generally, as the same technology node, they will be smaller than SRAM. I have to emphasize, as the same technology node, okay? Because SRAM today, available at 3 nanometer, but many of those emerging memories are not there yet. They're like 28, 22, 16 nanometer. So the F itself is different, then it's hard to compare, right? So if you use the same technology node, then of course, emerging memories generally better than SRAM, but still they are not the DRAM or the flash density. Okay, so it's very difficult. There are some opportunities, but then it's very difficult to directly compete with the DRAM and flash in terms of the density, or in other words, cost per bit. So that's why initially most of those memories are positioned as embedded memory, okay, to compete with SRAM on chip, or maybe some eFlash on chip, embedded flash on chip. But some special version of those memories could potentially go to the DRAM and the 3D NAND space, but that needs special engineering. But normally, they are not there yet. So here then the voltage typically a little bit higher than the SRAM, but much lower than the NAND flash, because NAND flash is more than 10 volts, even 20 volts. So those emerging memories typically 1 to 3 volts, you can make it work. And then the read time typically is fast, less than 10 nanoseconds, depending on the resistance. So typically it's okay, a few nanoseconds to 10 nanoseconds you can read. But then the challenge is the write time you see here. Most of them, because as I said earlier, you move the atoms, then the write time, typically you need tens of nanoseconds, even 100 nanoseconds. This, of course, is faster than flash, but then it's not as fast as your SRAM. SRAM is just 1 nanosecond or even below that, at most 2 or 3 nanoseconds, even if it's not level cache. So generally, those are slower than the SRAM, maybe comparable to the DRAM, but yeah, that's the speed. Okay. Only let's say exception here is the STT-MRAM could potentially be very fast, even below 1 nanosecond has been reported for the STT-MRAM. But then the current density is very high. You need to pass a lot of current to get that. So the retention, because most of those emerging memories are emerging non-volatile memory. That means they're non-volatile, means potentially they could be up to 10 years at 85 degrees C. But of course, you can trade off a little bit depending on the application. You can trade off, let's say, lower retention, faster speed, and lower write energy. That's possible. And then the endurance, okay. Endurance has a wide range for those emerging memories, typically no longer than 1E12, okay. And in many cases, only like 1E6, okay. So this is a little bit better than the NAND flash, because NAND flash, as I told you before, nowadays only 1000 cycle, 1E3 cycle. So this is better than flash, but it's not as high as SRAM or DRAM, because moving the atoms still somehow damage the system, the material property. So this is somewhere in the middle. It's kind of awkward. It's not that low. It's not that high. That really means you're depending on your application. So here's endurance is write endurance. How many cycles you can write? Okay, if it's depending on your application. If your application is read intensive, then no problem. But if your application is write intensive, then those emerging non-volatile memories will suffer. Okay. So then the write energy, many of those write energy is large, because as I said earlier, moving atoms compared to moving the charges, typically they are on the order of picojoule, okay. With the exception that FE-FET, because it's field driven, as you integrate the ferro into the gate stack, then you do not pass the DC currents. So it's electric field to flip the dipole. Then the power consumption is low. But other memories, like phase change memory, especially phase change memory, as I said earlier, you need to locally heat up that material, right, to melt the material. So you need to pass large current to do the Joule heating. So that's why the energy consumption to write the data is very high. So there are many trade-offs, as you can tell from this table. So none of them are perfect. That's why none of them, I would say, has a big commercial success so far. Okay. Some of them are in the volume production for certain applications, but they are not, changing the landscape of the SRAM, DRAM flash yet. They may find new applications or let's say new applications or supplements with some of the existing mainstream technology. But if anyone say, okay, any new memory will replace the existing, they are making jokes. Okay, impossible. Okay, to replace SRAM DRAM flash at least I would say 20 years from now. Okay, because those emerging memories has been there more than 20 years already. I started working on the RRAM 15 years ago. 15 years ago, I was one of the pioneers in the community to work on the RRAM. If you look at the citations to my IEEE fellow recognition, I was cited for the contributions to make the RRAM, kind of successful, because right now it's offered by TSMC in the production, and we did some early work in the RRAM space. But anyway, so it's difficult, as I said. Okay, so any questions?
Your tangential question, but you mentioned how DRAM and Flash have their own foundries.
Mm-hmm.
So even the emerging technologies, is it like completely different, or can that be combined with the silicon?
So that's why I said earlier, many emerging non-volatile memories are targeted at the embedded memory space. Embedded means with logic, right? That means the logic foundries are offering that. That means you have the flexibility to design and tape out and then, innovate there. For example, TSMC offer phase-change memory, RRAM, STT-MRAM. Yeah, it's all in their platform, on their platform. And designers can do that. Of course, university researchers may not have access to that, but commercially, they have the offering. So yeah, I would say more opportunities exist with those emerging memories here, right? So the foundries, for example, STT-MRAM, all the major foundries offer that. Not only TSMC, Intel has that, Global Foundry has that, Samsung has that. It's all available. Yeah. Okay. So here, as I said, there's no way to get rid of the SRAM, DRAM flash, but there are some opportunities for, changing the memory hierarchy by introducing those new technologies. For example, here, the RRAM phase-change memory and even FE-FET are suited as these embedded memories. Okay, embedded memories, especially for the automotive electronics. Okay, because many automotive products use the MCU microcontroller. Microcontroller has the NOR flash or embedded flash, eFlash on chip. There are like a few megabytes data you have to store on that microcontroller. And then the eFlash does not scale beyond 28 nanometer. So your technology here, if you can scale beyond 28 nanometer with non-volatile storage, this is a easy market to enter. Okay, that's why all the major foundries initial targets is to use RRAM, phase change, even FE-FET for this embedded memory in automotive space. And they got a lot of customers actually. TSMC sent, for example, if you read the tech news, Infineon's latest microcontroller has TSMC RRAM in it. Okay, so TSMC got a big order from Infineon or maybe other automotive makers, for example. besides Infineon, there's NXP, TI, and so on, all kinds of companies. And from Japan, Renesas and others. ST-MicroElectronics has a phase change memory. All those, automotive and microcontroller makers are using those emerging memories right now. The market is, of course, not as large as NVIDIA and AMD, but still is a sizable market there. For example, even the NOR flash, what is the market size? NOR flash. So I'm talking about the standalone NOR flash. I got a number from one of my friend from Macronics, who is one of the major vendor of the NOR flash, standalone NOR flash. It's more than 5 billion a year. So it's, of course, it's not hundreds of billion or trillion, but still it's a sizable market there. Okay. So that's the initial target, okay, for those emerging memories. And then there's a potential to replace NAS level cache with STT-MRAM, SOT-MRAM, because they have kind of longer endurance compared to the others. And especially if you are looking into automotive again, or even aerospace application, because aerospace, as I said earlier, the SRAM, suffer from the radiation effect, right? But many of those emerging memories do not have that problem. So you may have some niche applications for those emerging memories in the cache, NAS level cache space. Okay. So here, then there's a storage class memory concept proposed, like even more than maybe 15 years ago from IBM, to create another level between the main memory and the storage SSD. So in this space, for example, Intel and Micron tried like 3DX points with phase change memory, right? This Optane SSD, which you could buy, a few years ago on the market, is positioned as a high-end SSD. Its performance is better than your normal SSD, like faster, each read-write speed or faster, bandwidth higher, and it provides you a non-volatile memory storage, 10 years lifetime, and so on. So that was attempt, right? Of course, then later we will discuss why it failed in the business, but that was attempt. But still, there's people are not giving up, even though Micron and Intel failed in that business, not because of technology, okay, because of the market and business, okay. So, for example, here there's a recent renaissance of this phase change memory in the 3DX point kind of architecture called the selector-only memory. This was pushed by SK Hynix and a few others. I think Samsung also jumped in. So people are not giving up, okay? They're still trying to do some, 3DX point kind of equivalent architecture to enter this market storage class memory. And also here, even for the NAND flash, okay, there is a proposal to replace the charge trap layer with a ferro layer. So you can do the 3D FE ferro VLAN. And SK Hynix has a research on that. Samsung has a research on that. And also here at Georgia Tech, we have research on that in collaboration with Samsung. We collaborated on this 3D FE VLAN. So there are many opportunities there. And also here, the multi-tier FE-RAM. Last year, Micron reported a 32 gigabit FE-RAM at IEDM conference. If you look at the spec there, it almost matched the LPDDR5 DRAM spec while providing additional non-volatility to the data. And the data retention, DRAM, you have to refresh every 64 milliseconds. But if you use this 32 gigabit FE-RAM, the same density as the DRAM, then you don't need to refresh so often, right? So it looks good. But still, business-wise, there are many challenges to overcome. But here we focus on the technology challenges first, okay? Business-wise, I cannot, help. Okay, so any questions? So here are some trends we summarized. And here I haven't updated this. This was till 2020. So if you look at the density, or let's say in terms of the overall capacity per die, per chip, okay, I'm not talking about you do the HBM bonding and you can get more. This is per single chip. So like the NAND flash already got like 1 terabit thanks to the hundreds of layers 3D not stacking 3D and it's monolithic 3D, right? And then you have the TLC, QLC. It's already 1 terabit. If you recall last lecture, all the chips today is 1 terabit per chip. And then the here, of course, if you do the stacking of HBM, this is earlier versions of HBM. You can get this 128 gigabits. This is bits and bytes, but per die, for example, LPDDR5 per die is only 12 gigabits. Today, the best is like 32 gigabits. So that is the capacity. And then SRAM, is like 128 or even at most 256 megabits. Yeah, around that level per die. If you do AMD like V-cache, you can stack. So emerging memory. So for example, like the largest MRAM is around 4 giga, maybe recently maybe a little bit larger, a few gigabits. You can have the MRAM. And then the phase change, if you do the 3DX points, you can get 16 giga or 32 giga around that. And RRAM, there was a report like a few years ago, also 32 gigabit RRAM. And then the Ferro is kind of a newcomer in the field. I mean, Ferro itself is not new. We'll talk about the history later. But the new Ferro, based on the hafnium oxide system, is a newcomer. And then at 2020, Sony demonstrated the 64 kilobits chip. But as I said, last year, Micron has a 32 gigabits FE-RAM from Micron. So that is a general trend in terms of the capacity. Those emerging memories can get up to like, around 10 giga to 30 gigabit per chip today. But that is mostly for the standalone. Okay, for embedded, like the automotive, you don't need like gigabits. Okay, there is on the mega level. Okay, this is up to gigabits, but not necessarily you have to do gigabits if you integrate on chip. Okay, with microcontroller, you don't need the gigabits. So if you normalize the density, that is a gigabit or megabit per millimeter square. Okay, I wish you to roughly, understand the numbers here. For example, the SRAM lowest density, right? Even though it has higher technology node, I mean, more advanced technology node, like 5 nanometer, even for 3 nanometer, because 5 to 3, the SRAM, if you recall, the scaling very, slow, right? Almost stop. It's no more than 40, so it's like 30 to 40 megabit per millimeter square. That is what you can get from the SRAM today. And then the MRAM, this 4 gigabit MRAM, I believe is from the company called Everspin, which was a startup company based in Arizona, Phoenix. Okay, it's no longer a startup. It has been there for almost 10 years or even more than that. So in their demonstration, then this MRAM could be around that level. Okay, at older technology node. Okay, it's not 5 nanometer, 3 nanometer. So they can get up to close to like 40 megabits per millimeter square, probably at 22 nanometer or something like that. Okay. So it's on the same order of the SRAM, but at older node, So then the DRAM, this is at 18 nanometer DRAM, 16 gigabit, but for today's, 18 is like one X, one Y node, maybe one Y node. But for today's one, X, Y, Z, A, B, C, today's 1B, 1C node, then this number is around like 300 to 400, no more than 400, roughly speaking, 400 megabit per millimeter square. Okay. And then the phase change memory from the Intel Micron's demonstration earlier. So they can get about 600 megabit per millimeter square. So you see that it's on the order of this MRAM. Okay. And flash, if you recall, more than 10 gigabits. And if you recall, last lecture is already 20 gigabits, more than 20 gigabits. Even the latest is like 30 gigabit per millimeter square. Okay. You can look at the density. That means, roughly speaking, the cost per bit, right? Within 1 millimeter square, how many bits you can pack, right? So any questions? Then in terms of the prototype, the chip speed, or let's say bandwidth. So here, this is another survey, read bandwidth versus write bandwidth. And for most emerging memories demonstrated so far, the bandwidth is around this corner. And I would say, so here, this red one is a flash, okay? Flash generally is like slow in write, but emerging memories could be faster in write. So that's why the write bandwidth, typically higher than the flash, but the read on the same order, or a little bit better, let's say, a little bit better. So if you really need a bandwidth, you have to go to the DRAM. That's why what AI is needed today, the HBM, right? So DDR5, you have to go from the DDR5 to GDDR and then to the HBM, right? This is a system level bandwidth, here. For the HBM3 is over terabyte per second, right? So that is a bandwidth. So that's why there's no replacement for the DRAM, as I said. That's why DRAM industry is so happy these days, right? Make a lot of money out of the AI, because NVIDIA's GPU heavily depends on the HBM, right? Heavily depends on the HBM and the packaging, because if you look at the tech news today, NVIDIA's Blackwell GPU, right, announced earlier in the spring, got delayed. They're supposed to, have it right now on the market, but they delayed for another 6 months or 8 months because of the HBM availability and also the packaging issues with, the processor and then the HBM and so on. So it's not about the processor is easy there. The challenge is this integration with HBM. Yeah. Okay, so then let's we have like 2 minutes left, but we can start here. Some technical discussion on the array architecture. So first one is 1T1R. So this is how you integrate this resistor-based, because many of those emerging memories, right, you see earlier, it's like a resistor, two terminal devices, where you can change the resistance, right? So if you want to integrate into the array, typically you need to have this transistor, access transistor, to select the individual resistor. It's typical, it's like your 1T1C, right, DRAM, or here you have 1T1R, because you have to locate this cell by the word line, control the gate of the access transistor, and then the source line, and then the bit line. Okay, so it's 1T1R. So here, typically the R to be integrated to the drain contact wire, on top of drain contact wire. And depending on the foundries, you can do this integration at lower metal, like between metal 1, metal 2, or you can do it higher level between metal 4 and metal 5, or even up to metal 6 and metal 7. Okay, depending on the process of a particular foundry. So here, in terms of the layout, right? Typically, you could do like 12F square in terms of 1T1R, but the most aggressive design, if you follow the DRAM, is like here, this is like you're standing a capacitor. If you use that kind of layout, you can go as low as 6F square, but that's very challenging, right? So you have to optimize everything for the DRAM. But typically they relax that, and then you can get like 12F square. There is a big assumption. So here, the minimal size, minimal W over L apply here, okay? But that may not be true. If your resistor here need large current to program it, you think your minimal transistor size not enough to provide the current. You have to increase W over L. If you increase W over L, that means it's become wider, right? Then your cell size will be more than 12F square, could be up to 50F square, which is true for the MRAM. So really depend on the current, how much current you need this transistor to deliver to the resistor in order to change the resistance. Okay. So here is a typical read-write scheme, right? If it's let's say the bipolar switching set, then you are going to apply for the selected cell. First, you need to turn on the wire line, turn on this transistor, and then you apply positive voltage to the bit line. So here you then current flow this way. Then you will program the device for the low resistance states. And then if you reverse the polarity, that means you apply reset voltage to the source line, then current flows the other way. Then you will reset the device. Okay, you can look at the bias condition. So that means there are still half bias, half select cell like this one, okay. And then for the read, then it's simple. So just turn on the wire line. And then here on the bit line, you have the read voltage, which is smaller than the set and reset voltage because you just want to read the cell. And then this current will go to the sense amp. Okay. So the challenge for this 1T1R scaling, as I said earlier, is mainly the switching current, the write current or programming current to change the states. So here, this was surveyed a few years back, and we look at the programming current for those phase change memory, STT-MRAM, RRAM reported in the literature. And especially you look at the phase change memory, you need very large currents, even hundreds microamp currents. And also MRAM, 200, of course, depending on the technology node, smaller tech node, generally lower currents. But still, this is a large, like hundreds microamp. This is larger than the, let's say, even W over L equals to 3. I forgot what is the technology node, maybe 45 or 32 nanometer technology nodes. But basically, the minimal transistor cannot give enough currents. So that's the main problem here. This is still true for today's phase change memory and MRAM and even RRAM. Ideally, they should reduce the programming current, okay, to tens of, even 10 micron. That would be perfect if it's 10 micron. But right now, typically it's like more than 100 micron. So you need a very large transistor to give the current. So next is the cross-point array. We will probably unable to finish that, but just some introduction. So why do we need this transistor here? If we can get rid of the transistor, that would be even more compact, right? So that will enable the 4F square cell density, right? Because here, if you only have this resistor, then you can have just the word line bit lambs, and then like F and F and F and F, then one cell, just a 4F square, like the 2D NAND flash, right? So the problem is that if you do not have this nonlinear element, the transistor give you nonlinear IV, that help to cut off the current of the unselected cell. Otherwise, if you have a system, let's say just with a resistor crossbar, this is called crossbar array because it's like word line, bit line, perpendicular. So this is called cross-point array or crossbar array. If you only have the resistor, when you apply current or apply voltage, then current will flow everywhere, right? It's a resistor network. If you do not cut off the current for the unselected cell, then the current will flow everywhere in the network. That will be a mess. So that's why you need something to cut off the current. So here in the cross-point array, you have to introduce this selector device. It's like a diode or bidirectional diode to rectify the current. So we'll talk about that more in the next lecture. The key elements, if you want to do this cross-point array, is that you have to have this selector in series of your resistor, okay? And also in this case, you need some high on-off ratio. So typically, STT-MRAM on-off ratio is not large enough. On-off ratio means the resistance ratio between high and low resistance states. STT-MRAM is pretty low, only like 2, maybe 2. Then due to this leakage path, it's very difficult to distinguish. So generally, for the cross-point array, only RRAM and phase change memory could be used there. So for STT-MRAM, typically you need the transistor to really cut off the sneak path or the leakage path. So we'll talk about that more in the next lecture. Okay, that will be after your midterm. Okay. All right.